Alright, this is the solution video for QQ2T number 2. So quantitative translation number 2. So it looks like we have a ball being dropped and maybe some sort of liquid. We have a mechanical energy lost versus stiffness. Oh boy. So maybe this is like an energy conservation problem type thing. So we have food scientists creating a new oil. At room temperature, the oil is a liquid. So as the oil gets colder, however, it stiffens or thickens into a sticky gel. To explore the properties of the oil, the scientists fill the container with the oil to a height D, as shown in the figure above. They drop a steel ball of mass M from rest at the top of the oil. Using video capture to capture the ball's motion, the scientists calculate the energy lost, or E lost, the mechanical energy lost by the ball earth system from the time the ball enters the oil to the time just before the ball strikes the bottom of the container. The scientists also define stiffness, S, of the oil as the quantity proportional to the force required to move a rod through the oil at the temperature of a constant speed. Okay. Scientists calculate E lost and S at several different temperatures, ranging from room temperature to the lowest temperature at which the ball still falls through the oil. The graph above on the right shows E lost as a function of S for the calculated data points. Okay, so it looks like that as stiffness increases, the amount of energy lost by the ball also increases, but until we reach some maximum. Now, the reason why we have that maximum there is because the system starts with a specific amount of energy. Since it's the ball earth system, we're probably going to start with the amount of potential energy here. So this E max represents the initial potential energy of the system. Okay. Now, if no energy was lost, all of this gravitational potential energy would convert to kinetic energy down here. Okay, but essentially what's happening is the ball is losing energy, so it's moving at slower and slower speeds as it hits the bottom of the container. Okay, so give a physical reason why the curve in the graph would not reach the vertical axis even if scientists had taken data over a broader range of temperatures. So they're saying, why doesn't this graph continue to essentially this axis here? Well, that axis here represents zero stiffness, which would mean you're moving through air. If you have oil, it's impossible to have zero stiffness, because there's something getting in the way. Even at the highest temperatures, there's still going to be some resistive force from that oil. So stiffness can never be zero. So that's going to be why we're never reaching that vertical axis. Okay, so the vertical axis represents zero stiffness, which is physically impossible. So the graph will never reach that axis. Okay, let's check the scoring guide and make sure I got that right. So I get 1 point for indicating that the axis corresponds to zero stiffness, and for saying that no measurement of stiffness could be zero. So I said that. Woohoo! Alright, question B. As S increases, E lost approaches some maximum value labeled E max. Write out an equation for E max in terms of M, D, and physical constants as appropriate. Okay, and then I need to justify my answer. So, D is this height. Ooh, so remember, we already talked about this. This E max is the initial gravitational potential energy. We can't have more energy in our system than the initial gravitational potential energy. So that Emax just is the initial gravitational potential energy, which is mgh, or in this case, using the variables we have, g, which is a fundamental constant, and then d, the distance that the ball travels vertically. That was easier than expected. Okay, so some of the scientists are trying to represent the relationship between the oil stiffness and the mechanical energy loss, and writes down the equation 2E lost is CS squared, where C is a constant with appropriate units. Another scientist points out that this equation cannot be correct. Give 2 reasons why the equation cannot be correct. So I need 2 reasons. Okay, so based on this equation, it looks like E lost is proportional to S squared. So if I was to graph a E lost versus S squared, I should see a parabola, which I see a sideways parabola, but not a regular parabola. So that's one reason why. The other reason why is that a parabola increases forever. We know that E lost has to reach some maximum value, and that equation doesn't reflect it. So there's our 2 reasonings. So this equation cannot be correct because it suggests E lost is proportional to S squared, which 1 does not match the graph of the data. I combined it of the data. And 2 does not account for a max value, as 2E max, or 2E lost, equals CS squared would increase to infinity, or essentially go on forever, so it wouldn't reach a maximum value. Okay, let's check my score. Ooh. So, part B, I get 1 point. Oh, I got that point. Okay, and then I get a point for stating. Oh, was there supposed to be an explanation for B? Did I not answer a question? I did! I didn't justify my answer, guys. Oh my goodness. Okay, so I have to justify my answer. Oh boy. So this is the equation for E max, because in the ball earth system, the initial energy is the max energy in the system and equals the potential energy of the ball. Okay. All right, now I can check my answers to B. So I get that max energy that can be lost is equal to the initial energy of the system. Initial energy of the system is gravitational potential energy. Whew! Almost lost out on 2 points. Don't forget those explanations if they ask you for them. All right. Question C. So I get 1 point for a statement that the equation does not match the graph. Yep. And 1 point that it demonstrates that E loss cannot increase indefinitely. I said that as well. So their example statement is, the equation indicates that E lost increases indefinitely with S, but the graph has an upper limit. The equation represents a parabola, which doesn't match the graph. It doesn't make physical sense that E loss could be more than the available potential energy. All right. Let's continue on with question D. So, further attempting to model the ball's motion through the oil, the scientists write the following equation for the time it takes the ball to fall through the oil. So they're saying T is Z over S, where S is the stiffness and T is time, and Z is some constant. So is this equation plausible? In other words, does it make physical sense? Okay, so Z is a constant that can't be changed. So this has shows an inverse relationship between stiffness and time. So if I increase the stiffness, the amount of time to fall through the oil should decrease, meaning it should fall faster. That doesn't make any sense. If I increase the stiffness, it should fall slower. It's harder to get through molasses than water. So this is not possible. Okay, so this equation shows an inverse relationship between time and stiffness, suggesting as stiffness increases, so I'm explaining what an inverse relationship means, time should decrease, which is opposite of what happens. What actually happens? All right, so let's check my points there. So I get no points for saying not plausible. So for a statement that, or implication that the equation indicates that as t increases, s decreases, yep, that's the inverse relationship. And for a statement or implication that t should be larger as s increases. So I said the opposite is true, which is why I get both points. All right, question E, last part. So question E says, delta K is the change in kinetic energy of the ball between the time it is released from rest and the time just before the ball strikes the bottom of the container. On the axis below, sketch delta K as a function of S in the oil stiffness. Okay, so remember, change in kinetic energy is really going to be a change in the ball's velocity. Okay, so as we have less stiffness, I would expect a large change in velocity, because zero stiffness here-ish would essentially be air, whereas, larger stiffness might be something like honey or molasses. And I would expect the ball to move very slowly through honey or molasses and very quickly through air. Very quickly corresponds to a larger change in kinetic energy, and honey and molasses corresponds to a low change in kinetic energy. Now, just like we talked about before, we're never going to reach this vertical axis because that represents zero stiffness, which if we have something in the container, then that's not going to be true. So I'm not going to touch the vertical axis. So my graph is going to look something like that. Okay? Where I have a large change in kinetic energy at small stiffnesses and a small change in kinetic energy at large stiffnesses. Okay, let's check my points. Scrolling down. Okay. So I get 1 point for concave up. So essentially any graph that is like a half a smiley face, even if it's backwards, okay, that approaches the horizontal at a higher S. So it does need to be this graph, okay? So there's my 1 point. That's what that first point is talking about. For having a maximum value of delta K at lowest graph values of delta of S, which can be S equals 0 or a positive value. So the fact that the graph approaches the vertical axis, that's another point. And then if delta K approaches infinity. Oh, okay. So they're saying this note here is important. They're saying that if you put arrows on your graph, you don't get that point. So don't put arrows on your graph. Okay. And then you get another point for high values of S. The graph approaches and does not cross the horizontal axis. So the sense that you have another asymptote at the horizontal axis. Now, if you cross it, that's no good. You don't get that point. But this note here says if the graph touches the axis without crossing it, you can still get that third point. Okay. All right. So this was definitely a strange way to think about energy conservation because you have a ball falling through oil. It's like a weird question. But this is how they like to test your ability to apply knowledge rather than memorize it. So they're going to present you with a unique situation that you've never seen before to apply knowledge that you know. Okay? This question was really not that difficult. Okay? But the part that makes it hard is you're presented with this idea that you've never seen. So remember, when you're approaching these problems, have faith in yourself. Figure out whether you might need energy conservation or work or stuff like that. Or, is it a momentum problem? Is it a forces problem? Even though it looks weird, you'll be able to kind of classify it as one of those. Okay? All right, see you soon.